Hello and welcome back. My name is Tarmo and I'm here to give you a short tutorial today on the normal distribution. On the screen behind me, I've simply pulled up something that I found online. It seems to me, looking up above, that it was posted on LinkedIn. But this figure is central to much of what we do in statistics. You'll find versions of this in your textbook. You'll find versions of this if you type in normal distribution online and look at any of the images that pop up. What this image tells us is that if we take any normally distributed variable and convert the values that we have for the observations into z-scores, then we standardize them into a distribution that has a mean of 0 and a standard deviation of 1. What does that mean? Well, it tells us what the shape of this distribution, or this curve, looks like. So if we look at all of the values that we have of our observations, they would fall somewhere along this x-axis. The mean here, once it's been standardized, would be 0, but you imagine if you took test scores from the midterm or the final exam in one of your courses, and if you were to calculate the z-scores of them and plot them in this kind of a graph, then the average score, the mean score that was obtained on those tests would be here in the middle. It just makes it easier when the mean is always 0, because then we can measure how far on the positive side or the negative side of that mean are we by measures of standard deviation. And if we think back to our data description, we know that if we have a larger standard deviation, there's more variability in our data. If we have a small standard deviation, the variability is constrained to a very small range. So what this allows us to do is, in a normally distributed variable, look at it and say, if we have data that's being normalized, we look at all of the values that are near the mean, okay, up to the mean plus 1 standard deviation or the mean minus 1 standard deviation, about 68.3% of all of our data will fall within this range. Obviously, if you have a larger standard deviation, it means you're covering a larger range of values. A smaller standard deviation means that the range of values is tighter. But still, 68% of all of the values, or 68% of the people that took the test, will have a grade between the mean plus or minus 1 standard deviation. What this tells us also is that if we went 2 standard deviations above the mean or below the mean, about 95.5% of all observations will fall within this range. So 2 standard deviations plus or minus the mean, 95.5% of all observations fall within that range. And if we go further, if we move out to 3 standard deviations, then 3 standard deviations plus or minus the mean, we're looking at 99.7, or almost 98% of all observations fall within this range, which means that it's really unlikely that you have values that are really high, more than 3 standard deviations above the mean, or less than 3 standard deviations below the mean. If almost 98% of your observations fall within plus or minus 3 standard deviations, that means only 2% of your observations are in these extreme ends of the distribution, or what we call the tails. We have the positive tail over here on the right, and the negative tail here on the left, which mean that they're relatively extreme values. So you may have had somebody that scored really, really, really well on the test relative to everybody else, or really, really poorly relative to everybody else, and they would fall into one of these ends. So this is a way to think about what our expectation is for our data, given that we have this. Now, the really nice thing is, because the shape and size of this distribution is really well known, we can start to do some interesting things with this distribution, and I would like to show you that. I'm going to move this out of the way and I am going to expose a piece of software here that you may or may not have been exposed to before. It's called R. It's free, it's open source, it's designed for statistics. It does way more than just statistical analyses, and we're not going to be using it in this course, but I created a small piece of computer script that allows us to visualize some things. So I'm going to use it here to demonstrate what the benefit is of using the standard normal distribution, because we know the area under this curve. So we need to think about area being the same as probability. These concepts go together and they start to allow us to do some interesting things. So you can imagine if you have 50 people in your class and everybody writes the final exam and everybody gets a grade, then we have 50 grades that are going to be plotted in this once they've been normalized. If you think about counting how many people's grades fall in that distribution, well, all of them do. So you can imagine then that the area under this curve represents the probability of observations within the range of the extreme highest to the extreme lowest grade. What I've done here is I've shaded in gray the area under the curve, and what I've done, I'll just calculate it here again, the area under the curve here is 1, or 1.0000. We often round areas to 4 decimal places just to ensure that we have a really good representation. So it's saying that in this code is that from minus 10 standard deviations to plus 10 standard deviations. So if you remember, plus or minus 3 standard deviations, about 98% of your data. If you went to 10 standard deviations on either side, it's really likely that you've captured everything, although this curve is asymptotic, which means it never actually touches the x-axis. It continues indefinitely in either direction, but within rounding error, we have an area under this curve of 1.0, which means that all observations fall within this range. So we can think about that and say, well, if the area under the entire curve is 1, what is the area for all of the values, let's say, on one side of the mean? So let's look at that. So if we say, well, what is the area under the curve for being smaller than the mean all the way to sort of infinity on the smaller end of this distribution? Well, the area would be 0.5. Obviously, it's half of the curve, so 50% of all observations will fall within this region of the graph. We could do this the other way, and we could say, well, what if we went from 0 to plus 10, and we're looking at the area on the positive side or on the right-hand side of this graph, and we're saying, well, here we are 50% of all observations are on this side of the distribution. And that makes sense. I mean, half of them are going to be on one side and half are on the other. The mean is directly in the middle. Now, the graph or the diagram that I showed you from LinkedIn said plus or minus 1 standard deviation, plus or minus 2 standard deviation, plus or minus 3 standard deviations across the bottom. I have here Z scores or Z values. So these are 1 Z score, 2 Z scores, 3 Z scores, 4 Z scores smaller than the mean, or 1 Z score, 2 Z scores, 3 Z scores, 4 Z scores larger than the mean. The two things are used interchangeably. So here when you see a Z value of minus 2, it means less 2 standard deviations than the mean. But this is really, relatively simplistic. Area under the curve is 1, area under half of the curve is 0.5, but we can carve out any sort of vertical cut through this distribution and find out what is the area under the curve in one tail of the distribution. So what if we went to minus 10, but we go to, let's say, we're now looking at the area from a z-score here of -1, or 1 standard deviation less than the mean, all the way towards the low end of the distribution. What is the area under this curve, or what is the probability of the number of observations that we're going to find in this part of the distribution? And here we see that we have 0.1587 as a probability. So about 15 or 16% of all observations are going to be on this end of the curve. So these are mirrored on two sides, so you can imagine that if we looked at being 1 standard deviation or larger, then we should have about 15-16% on that side. So 15-16% on either side, you add those together, and you're looking at 32-ish%, and now it's leaving you with 68% in the middle. The same thing that we saw before when we said, well, what's the probability or the number of observations within the range in the middle? But we can say, well, what is the range or the probability in the tails? So let's keep going farther out. Rather than starting at 1 z-score, let's go to 2 z-scores. And now this is starting to fall behind my shoulder, so I'm just going to go up. The area here that's shown in gray from 2 standard deviations less than the mean and smaller values, we're looking at just over 2%. So the values are starting to get smaller as we get into the tails, but we know that if the area in this end of the tail is about 0.02 or 2%, then the area here that isn't shaded in should be 1 minus this, or about 98%. So we can calculate the areas under the curve if we know this value at which we want to cut the distribution. And the great thing is that these values are all easily obtained from tables, but I'm going to show you in Excel that we can calculate them also very easily using some simple functionality, so that you can cross-reference whether or not you got the values from the table correct, and vice versa, so that you will always have many ways by which you can corroborate your answer before going on any further. So one of the classic things that we see is negative 1.96, and we see that about 2.5% of the distribution is in the tail, and the remainder then will be not in the tail of this distribution. So these values, this negative 1.96, these are the z-scores, or the number of standard deviations less than or greater than the mean that define some critical value from which we can then measure the area in the tails of our distribution. And when we do that, we get a probability of how likely is it that a value is in the bulk of our data, or is it in the tail. And if it's in the tail, remember, we're far from the mean, so we're less likely to occur. So if we find that values occur out in this region here, they're relatively extreme, and they might be beyond what we are expecting for our data set. So the key things to remember: the area under the curve is always 1. Once we decide where to slice or where to cut our distribution, we then identify the tail either on one end or on the other, or on both, and we can get the area in those tails. Those give us a probability of falling within that tail. That is, how many observations do we expect? And if that number is really, really small, then it might be rare. So what I'd like to do is then bring us back to Excel, because this is the environment that we're going to be working in. And I remind you that we're working with what's called the Z distribution. It's the standard normal distribution. So when we have normally distributed variables, we can calculate z-scores. That is, we can transform all of those measurements, be them test scores or something else, we can transform them into a standard normally distributed variable using the formula for a z-score, and I have it written out here. So sometimes we refer to z-scores or z-values, and we have x minus mu over sigma, and x is our data value. It's the test score that you might have. Mu is the mean or the average test score for that class or that group. And we have the standard deviation. And these things we all learned to calculate back when we talked about data description. When we take the data value and we subtract the mean and we divide all of that into the standard deviation, we end up with a z value. We do that for all of our values in our data set. We now have a distribution that is normally distributed. It follows the standard normal distribution. So in Excel, there are a whole series of calculations that we could make. I'm going to show here the three that are the most common and the ones that you're likely going to end up using. Let me see if I can zoom just a little bit more here. Yes. Okay, so if we want a z value, okay, we use norm.inv, given that we have a probability, a mean, and a standard deviation. That is if we're dealing not necessarily with standard normal distribution. So this is sort of beyond what we're talking about right now. So let's focus on this version right here. If we know the probability or the area under the curve, then we want to know what is the z value that cuts off that tail. So where does that vertical line in the distribution exist so that the shaded area of the tail has the area that I'm interested in. So we take that p or that area, we run that through norm.s.inv, and it will give us the z-score. We can work the other way, where maybe we want the area or we want the probability given that we already have a z-score. So if we have a z-score and we're mean and a standard deviation, we use norm.dist to give us that value. So I've got some worked examples here on the right hand side. I'm just going to scroll up just a bit. So given a z value, find the corresponding area in the tail or in the tails. So if somebody gives you a z-score, the z-score is 2.87, then the area in the left tail will be this, and the area in the right tail will be that. Remember, this z-score is positive, so it's going to be on the right-hand side of the mean, which means that when we cut off, and we're almost 3 standard deviations larger than the mean here at 2.87, so we're really quite far out, that means the area in the right tail is going to be really quite small relative to a lot of area that's left on the left-hand side. If the z value was negative, then in our distribution we would be cutting at the sort of low end, and we would have a smaller area in the left tail and a larger area in the right tail. So let's take a look here. If I change this to negative 2.87, we notice that these two values just swapped, and the lower area now in the left tail and the larger area in the right tail. If I take these two and I add them together, I should get 1. So let's take a look at that. Equals this plus this, and sure enough, the total area under the curve is maintained at 1. If I look at how these are calculated, we're using norm.dist. We're taking the z value from here. We have a 0 mean and a 1 standard deviation for a standard normal curve. Same thing happening over here, but rather than calculate it all over again, I'm just going to take 1 minus this. It's going to give me the remaining area under the curve. And we can change this to be anything. So if the z value is the mean, that's 0, it's right down the middle. Notice that half of the area is in the left tail and half of the area is in the right tail. If my z value is 1 standard deviation larger than the mean, then the area in the left tail, because I have my distribution, I have my z value to the right of the mean, which means that the area on the left tail is going to be bigger and the area on the right tail is going to be smaller. The nice thing about having it set up this way, you can type these things in and get the values really quickly and check things as you need them. The next example is that rather than having a z value and trying to get an area, we have the area and we want to work the other way to get the z value. So if I say that the area on the left is this, then I can figure out what the area on the right is by simply subtracting it from 1. So these two together, if you don't believe me, this plus this has a total area of 1. And when I have set this up, it tells me then somewhere there needs to be somewhere where this distribution is cut. The z value tells me where that happens. Here it happens at z value of negative 0.5, so it's half a standard deviation less than the mean, or almost 0.6 standard deviations less than the mean. You can see that norm dot inverse, all we're doing is specifying the area. We have the mean and the standard deviation 0 and 1 for a standard normal distribution. Works really nicely, and they're all linked together. If I went here and I changed that to 0.5, then I know that if the area in the left tail is half and the area in the right tail is half, then I know that I must be right in the middle of the distribution where we have the mean and it's 0. If you type these in and it works and you get these values, then you know that your calculator is working properly. So we can use this, and we will use this to answer statistical problems. And we need to understand the area under the standard normal distribution is always 1, and what we're usually doing is carving off some piece of the tail, and we're trying to calculate the area or the probability in that tail. So thinking about this, playing around with the numbers, visualizing it, thinking about what that area and that z value mean will mean that the things that we do afterwards are going to be a lot easier. So take a look at this stuff, practice with it, work with it, and we'll talk again real soon.